Hi, I'm going to do a little Hermitian form series. Today I want to talk about the basics. And so let's start with what a linear functional is. As a reminder, if you haven't seen it before, I guess it wouldn't be a reminder then. It's a linear map, and it's a scalar valued map. It takes vectors to scalars. So if it's a complex vector space, it's going to take vectors to complex numbers. And so that's a linear functional. And here's an example. Just any linear combination of complex numbers will be a linear functional on C3. Bilinear forms are similar to linear functionals, but instead of having one input, we have two inputs. And it's linear in both inputs, or both coordinates. So you can use that linearity. Think of the z here as fixed, and you can just split this up into b of cxz and b of yz, and then take out the c. And you can do the same thing in the second variable. So here's an example of a bilinear form, the dot product. So you just multiply the like coordinates and add those together, and that will be a bilinear form. Sesquilinear forms are similar to bilinear forms. I changed all the b's to h's here because we're going to use Hermitian forms in just a moment. So sesquilinear forms are similar to bilinear forms, but they're conjugate linear in the second variable. So they're not linear, you can't pull out a constant, but you can pull out the conjugate of a constant. So in the first variable it's the same, but in the second it's conjugate linear. So that's what a sesquilinear form is. And a Hermitian form, which is what we're going to be talking about for a long time, is a sesquilinear form such that you have this conjugate symmetry on the form. So h of xy is conjugate, the complex conjugate of h of yx. And a Hermitian space. I know we got a lot of terminology here, sorry for that. Hermitian space is you got a vector space along with a Hermitian form. So we're going to be using Hermitian spaces in this little series. So inner product spaces are Hermitian spaces. So if you're familiar with inner product spaces from analysis or maybe algebra as well, those are Hermitian spaces. Is a Hermitian space always an inner product space? Can you think of, from everything that you've learned so far about Hermitian space, which is, I know it's very vast, can you think of the axiom for inner product spaces that may not be satisfied for Hermitian spaces? I'll share what that is later if you can't. So here's an example of a Hermitian space. It's also an inner product space, Hilbert space. So Hilbert spaces by definition have inner products. So L2, for instance, that's our go-to Hilbert space in analysis. And little L2 is a set of sequences that when you sum up the terms in absolute values, you get it, and you square them. The sum of the squares in absolute values is finite. Those sequences that satisfy that make up the set L2. And here's how the inner product on that set works. You just take each coordinate and multiply by the conjugate of the same coordinate for the other vector or the other sequence, and so forth. So that's an example of a Hermitian space, a Hilbert space. Another example is CPQ. CPQ is also a Hermitian space. So CPQ is, so you're familiar with Cn or Rn, where you have n copies of C or n copies of R. CPQ is very similar. It has dimension p plus q. So it's kind of like C of p plus q, but we're thinking of the first p coordinates and the last q coordinates as being separate. And here's how the form works. That's the vector space. That's how it works as a vector space. But remember, to be a Hermitian space, it's got to have a Hermitian form, and here's how it works. So you take each coordinate, the like coordinates, and you multiply those together, except for the second vector, you got to take the conjugate, complex conjugate, and you just add those up. And you do that for the first p coordinates, but for the last q coordinates, you need to subtract all those. So you don't add anymore, you subtract. So you think of these guys as positive and these guys as negative. And just a little calculation here shows that that is a Hermitian form. Notice that if we fixed p and q to be 1, we would have c of 1, 1. Then we have this vector 1, 1. And when we compute the Hermitian form of that vector with itself, we get 0. That's kind of unusual because the vector itself is not 0. So non-zero vectors that satisfy this property we call isotropic vectors. So v here would be an isotropic vector. The inner product with itself is 0. So for inner products, you don't have any isotropic vectors. Because remember, for inner products, the only way you can take the inner product of an element with itself and get 0 is if the vector itself is 0. So that's the difference between inner products and Hermitian spaces. If there are no isotropic vectors, we call it an anisotropic space. So orthogonality, we can say two vectors are orthogonal straightforwardly enough if their form is 0. If you take b of vu and you get 0, we say that they're orthogonal. And similarly, you can talk about v being orthogonal to a subset of v if it's perpendicular to everything in that subset. U doesn't have to be a subspace here. It can just be any subset. So this is a very important term that we're going to use again and again and again. And there's multiple ways of describing it. So here are a couple. So the form is non-degenerate if any of the equivalent things are true. We can say these in different ways. V perp is 0. So what does that mean? That means that the set of elements that are perpendicular to all the other elements in V is 0. So basically, when you take the only element that when you take the form with every other element that's perpendicular to every other element, the only one that satisfies that is 0. And 0 does satisfy that. Here's another way to say it. The only element that takes everything to 0 under the form is 0. And we're going to use this notation a lot. And this is what we mean by that. We say the radical of the form is 0. We also have the term degenerate, meaning that it's not non-degenerate, meaning that there must be some non-zero term that takes everything to 0. So here's a quick little proposition. If we have a Hermitian form, but it doesn't necessarily have the property of being non-degenerate, which is a good property, we kind of want that property, that's good, then even if it's not non-degenerate, we can get an induced Hermitian form or Hermitian space that is non-degenerate. And what we do is we define a new Hermitian form on the quotient with all the bad stuff. So radical h, you can consider that kind of the bad stuff. That's the things that are non-zero, but they're taking everything to 0. Well, if we take v and we mod out by those, we're setting all those things equal to 0 in the new space. So then our new space, v tilde, which is a quotient, is going to have the good property of being non-degenerate, because we've set all those bad elements to 0, and so now everything works the way we want it to. So here's how the new form works. So the new form is defined on equivalence classes, v and w. And the way the form works is you just take the original form and evaluate over those representatives from each of those equivalence classes. So we need to check if this is well defined, because if we take two different representatives from each of these cosets, we've got to make sure that this map makes sense and is the same regardless of which representative we choose. So that's what it means for it to be well defined. So if I have two different representatives from the same coset or the same equivalence class, then I evaluate our new form over those cosets, and by definition this is this. And now I can use the trick to break v1 up to v1 minus v2 plus v2. That's the same thing as v1. And then I can use the linearity in the first variable to split that up into a sum of two things. Remember, thinking of that w1 as being fixed. And this equals 0. Why does this equal 0? Well, remember that if v1 and v2 are in the same equivalence class, then their difference must be in the 0 equivalence class, or their difference must be in the subspace that you're modding out by, in the quotient. So if v1 and v2 are in the same equivalence class, then their difference must be in the radical. And what's the radical again? That's all the set of elements that take everything else to 0 under the form. So v1 minus v2 takes everything to 0, so it definitely takes w1 to 0. And that's why this is 0. So we get this, and then just using our definition up here, this equals this. So what we've done is change this v1 through this little manipulation. We change it to v2, and we can do the same trick for the w's and change that to a w2. So what we've shown is, regardless of which representatives we choose from each coset, we get the same value for the form. And that's good. That means it's well defined. The other kind of trivial part of checking that a map is well defined, well, at least in this case, is showing that it does take values into C. It is complex valued. But we really don't need to worry about that, because the way we've set up the map, whatever you choose in here, it's defined by this form here, which does map into the complex numbers, so we don't have to worry about that. So it's well defined. Let's check that it's non-degenerate. What does it mean to be non-degenerate? It means that the radical is 0. But in this new space, for the radical to be 0, 0 is the equivalence class of 0. So we need to check what elements send every other equivalence class to 0. And hopefully that will only be the 0 equivalence class. So let's say that this equivalence class v tilde takes every other equivalence class to 0. Then by the definition, h of vw equals 0. And it doesn't matter what representative you choose from the coset, because we showed, remember, that it's well defined. And you can choose any coset. So v actually sends everything to 0. What does it mean for v to send everything to 0? That means that it's in the radical. So hopefully we're getting a little comfortable with using this term. And what does it mean to be in the radical? Well, we're modding out by the radical, so that is 0 in the quotient. So that is the equivalence class of 0. So we showed that if something is in the radical, then it must be 0. And that's what it means to be non-degenerate. Next thing I want to talk about is the hyperbolic plane for Hermitian spaces. And here's how it works. You got two complex dimensions, C2, and we're thinking of it as a complex vector space. And if it has a basis of two elements that satisfy this property here, where h of xx is 0 and h of yy is 0, remember this can't happen in an inner product space, but it can for Hermitian spaces, and also h of xy equals 1, then this is called a hyperbolic plane for Hermitian spaces. So we're going to make two observations about the hyperbolic plane. The first is that it's non-degenerate, and we can see that it's non-degenerate by just checking a calculation in general between two elements in V. So this is a two-dimensional vector space, so each element is a linear combination of those two basis elements, and it splits up into 4, just like this. Now h of xx is 0, so do you see why that implies that h of ax cx is 0? If we just pull out the a and we pull out a conjugate of c, then we're going to have times 0, and that's going to be 0. And similar to this here, that will also be 0. And here we just pull out each constant, and we get this right here. And we know h of xy is 1, because that's how we defined it. And h of yx, that's also 1. Why is that 1? Because h of xy is the conjugate of h of yx. And the conjugate of 1 is just 1. So in general, the form works like this. Now, if this were in the radical, then this would take all these c's and d's to be 0. So if I chose d to be 1 and c to be 0, then that must mean that a is 0, mustn't it? And if I chose d to be 0 and c to be 1, then that must mean that b must be 0 as well. So it's non-degenerate. And the other sort of trivial observation we're going to make is that it's isotropic. And remember what it means to be isotropic? It's got some vector that takes itself to 0 under the form. And we've got two vectors that satisfy that, which is more than the one that we need. So we've shown that hyperbolic plane is non-degenerate and isotropic. And as it turns out, this is good enough for a definition of the hyperbolic plane. This actually, we have the reverse implication as well. So if it's non-degenerate and isotropic, then you can find a basis that satisfies the properties that we originally gave as the definition. So we already proved the 1 implies 2. So let's look at the other direction. If we know it's non-degenerate and isotropic, then there's a non-zero element that sends itself to 0 under the form. So we've got our x already. We've got the hxx equals 0. Now, v is non-degenerate, so it can't send everything to 0, because that would mean that it's in the radical. And that would mean that you have a non-zero element in the radical, but since v is non-degenerate, you don't have any non-zero elements in the radical. So it has to send something to something non-zero. And then we can scale that something so that h of xy equals 1. You might need to divide y by the conjugate of h of xy. Then, this is a little trick I learned from Jacobson's Basic Algebra 1 book. If you take that y and you replace it with y minus a half h of yx, then that turns out to work. So we got a basis of two elements, and they both satisfy these three things. So that's a hyperbolic plane. It's a non-degenerate and isotropic subspace. And it has a basis that looks like this. And that's all I got for today. and hopefully I'll come out with a new one soon. Thank you for watching. Have a good day.